Good day everyone! Welcome back to General Mathematics. It is still me, Engineer Omengan, to teach you exponential functions. Welcome to Exponential Function LBVG Math 1-4.4. In this topic, our most essential learning competency represents an exponential function through its A. Table of values, B. Graph, and C. Equation. The topics covered in this video are table of values of exponential function, graph of exponential function, parts of exponential function, and characteristics and restrictions in exponential function. For our learning objectives, by the end of this video, we want to learn how to graph an exponential function, supply missing values in a table of values of exponential function, determine the parts, trends, restrictions, and characteristics of an exponential function. Now let's go to the representation of exponential function. We have three ways. First is the table of values, second is the graph, and third is the equation. But mostly we will focus on the table of values and graph. Let's recall that exponential function is a function whose value is a constant raised to the power of the argument, especially the function where the constant is e. And it is represented by f of x equals a raised to x, where a is any constant number greater than 0 and not equal to 1, and x is the argument. But in this part of our lecture, we will focus on the restrictions with a, and that is, it should be a constant number greater than 0 and not equal to 1. So before we proceed, let's first discuss what happens if the exponent is negative. By laws of exponent, for example, we have here a raised to negative m, then we can express that as 1 over a raised to m. Our steps: first, we take the reciprocal of the base and remove the negative in the exponent. So, from this example, we take the reciprocal of a, and that is 1 over a. And then instead of negative m, we remove the negative sign and remain m. And second, we perform the operation. Or in other words, we distribute the exponent to the numerator and denominator. Let's have an example. Let's say we have here 5 halves raised to negative 2. First, we take the reciprocal of the base, and that is 2/5. Then, we remove the negative sign, so instead of negative 2, we have here positive 2. Next, we distribute the exponent to the numerator and denominator, that is 2 squared over 5 squared. And that gives us 4 over 25. Now let's see what happens when a is equal to 0. Let's remember that by laws of exponent, if we have a raised to negative m, that is equal to 1 over a raised to m. So for example, we have a equals 0, and m is a negative number, let's say negative 1. We will have 0 raised to negative 1 equals 1 over 0 raised to m. And let's remember that any number divided by 0 or with denominator as 0 is undefined. Therefore, for any negative exponent, function will be undefined. Let's take a closer look. Determine the outcome of the function f of x equals 0 raised to x given x is a set that contains negative 2, negative 1, 0, 1, and 2. If we have x equals negative 2, our f of x will be 0 raised to negative 2, and that is undefined. Again, if 0 is raised to a negative exponent, that will be undefined. Likewise with negative 1, 0 raised to negative 1 is undefined. However, 0 raised to 0 is 0. 1 raised to 0 or 0 raised to 1, that is still 0. 0 raised to 2, and that is still 0. Therefore, for any negative exponent, the function will be undefined and 0 elsewhere. Now let's graph our function. I will be using this Desmos graphing calculator. Just go to www.desmos.com/calculator. And in this calculator, we can graph our functions. So from our example, we have f of x equals 0 raised to x. So we can see here that for any values of x less than 0, that is our negative x-axis, we don't have any graph. And that is because for any value of x less than 0, it makes our function undefined. Thus, for our graph greater than or equal to 0, we have 0. Alright? And obviously, our graph here is just a straight line that is overlapping with the x-axis. Because if we can remember, our x-axis is y equals 0. Now let's see what happens when a is less than 0. So in this example, determine the outcome of the function f of x equals negative 2 raised to x, given that x is a set that contains negative 2, negative 1, 0, 1, and 2. So here, we can see that our base is negative 2. Okay, so let's substitute. If we raise negative 2 to negative 2, that is 0.25. Negative 2 raised to negative 1, that is negative 0.5. Negative 2 raised to 0, that is 1. Negative 2 raised to 1, that is negative 2. And negative 2 squared equals 4. So there is no obvious pattern here. Although from 0.25 to negative 0.5, that decreases. From negative 0.5 to positive 1, that increases. From 1 to negative 2, that again decreases. And from negative 2 to positive 4, that increases. What pattern we are looking for is that it should only be increasing or decreasing. However, in this function, it is a combination of the two. Now let's graph our function. But instead of just typing our function, let's first plot the point. So if we have x equals negative 2, and we raise negative 2 to negative 2, and this is that point, negative 2, 0.25. Next, if we have x equals negative 1 and raise negative 2 to negative 1, and that is this point, negative 1, negative 0.5, obviously it decreases. So let's type another point. We have 0, negative 2 raised to 0, and that is this point. So again, it increases. Next, if we have x equals 1, that is negative 2 raised to 1, and that is this point, 1, negative 2. And next, if we have x equals 2, that is 2, negative 2 raised to positive 2, and that is this point. So obviously, it decreases, increases, decreases again, and then increases. This does not make any sense. So even our calculator will not be able to graph this. So let's try it. So we have f of x equals negative 2 raised to x. We can see here that this graph does not appear in this plane. That is because even our calculator cannot find any pattern. Alright? Now what if a is equal to 1? So at this example, determine the outcome of the function f of x equals 1 raised to x given that x is a set that contains -2, -1, 0, 1, and 2. So let's substitute these values of x. So 1 raised to -2, that is 1, because 1 raised to any number is 1. So if we raise 1 to -1, that is still 1. 1 raised to 0 is still 1. 1 raised to 1 is still 1. And 2 or 1 raised to 2 is still 1. Therefore, we can say that for any value of the exponent, our function, or y, will always be equal to 1. Now, let's graph our function. So we have here y, or f of x, equals 1 raised to x. So we can observe here that the graph of f of x equals 1 raised to x is just a straight line, because for any value of x, the value of y will only be equal to 1. So that is just a horizontal line at y equals 1. Now let's move on to the parts of the graph of exponential function. So let's have an example. Determine the outcome of the function f of x equals 2 raised to x given that x contains the value -2, -1, 0, 1, and 2. So let's substitute. 2 raised to -2 is 0.25. 2 raised to -1 is 0.5. 2 raised to 0 is 1. 2 raised to 1 is 2. And 2 squared is 4. So obviously, we can see a pattern here that as x increases from -2 to +2, our y as well increases from 0.25 to +4. And that is because it satisfies the restriction that a should be greater than 0 and a is not equal to 1. Now let's graph our example. So instead of just typing the function, let's plot our points. So if we have x equals -2 and we raise 2 to -2, so that is this point, -2, 0.25. Next, if x equals -1, so 2 raised to -1, that is this point, -1, 0.5. Next, if x is equal to 0, so 2 raised to 0 is 1, and that is this point. Next, what if x is equal to 1? That is 2 raised to 1. That is this point. And last, from our example, what if x is equal to 2? That is 2 squared, and 4, that is 4. So that is this point. So we can see here that there is one trend. So from low value to a higher value. So from 0.25 as our y to +4 as our y. So when we connect these lines represented by our function f of x equals 2 raised to x, all of these points are on this graph or on this curve. Therefore, we can say that these points are part of this function. Now let's move on to the parts of our graph. So let's erase these points. Let's say we have f of x equals 2 raised to x minus 2. This is the graph of this function f of x equals 2 raised to x minus 2. These are the following parts of our graph. So we can see here that this graph passes through the y-axis and the x-axis. So at this point, where the graph passes the x-axis, that is this point, 1, 0, this is what we call the x-intercept. Again, the x-intercept is the point wherein the graph passes through the x-axis. So likewise, where the graph passes through the y-axis, that is what we call the y-intercept. Alright? So there's another part of our graph, and that is the asymptote. The asymptote is the imaginary line that our graph approaches as it approaches to negative infinity. So obviously that is y equals negative 2. So let's try. This line is an asymptote to this curve. When we say asymptote, the curve or our graph and this line will just approach each other but will never touch each other. So we can see here, although it is not obvious here, but as we look closer, we can see that our graph and this line just approach each other. And if we look closer, see, they will never touch as they approaches negative infinity or even positive infinity in some examples. Alright, so that's the part of our graph of exponential function. So again, the parts of the graph of our exponential function are the following. So, where the graph passes through the x-axis, that is our x-intercept. Where the graph passes through the y-axis, that is our y-intercept. And the imaginary line that our graph approaches is what we call the asymptote. Later on, we will discuss further how to get the x-intercept, the y-intercept, and the asymptote of our exponential function. But for now, those are our parts. Now let's move to an example. Determine the missing data in the table f of x equals 5 raised to x minus 2, given that x is a set that contains negative 2, negative 1, 0, 1, and 2. So for x equals negative 2, we will have 5 raised to negative 2 minus 2, and that is 0.0016. For x equals negative 1, we have 5 raised to negative 1 minus 2, that is equal to 0.008. For x equals 0, we have 5 raised to 0 minus 2, and that is 0.04. For x equals 1, we have 5 raised to 1 minus 2, and that is 0.2. And last, for x equals 2, we have 5 squared minus 2, that is equal to 1. Now we can see a pattern here that as x increases, or from negative 2 to positive 2, it increases, our y also increases, or it has an increasing, or it is increasing in value. And that is because our base here is greater than 1. Now let's graph our example. So we have here f of x equals 5 raised to x minus 2. We can see here that as x increases, or from negative infinity to positive infinity, our y value also increases. So from some value approaching 0 to positive infinity. That means that as x increases, our y also increases. Another instance is this. What if our base is greater than 0 but less than 1? So for this example, determine the missing data in the table f of x equals 1/2 raised to x minus 2, given that x is a set that contains negative 2, -1, 0, 1, and 2. We can see here that our base is greater than 0 but less than 1, and that is some decimal point, but in this example, we use 1/2 or 0.5. So, let's substitute our x values. So we have 0.5 raised to -2 minus 2, that is +2. 0.5 raised to -1 minus 2, that is 0. 0.5 raised to 0 minus 2, that gives us -1. And 0.5 raised to 1 minus 2 gives us -1.5, and for x equals 2, we have 0.5 squared minus 2, that is -1.75. We can see here that as our value of x increases, our y value is decreasing in value. And that is because our base is greater than 0 but less than 1, or a decimal value. That is why our y value or f of x is decreasing. Now let's take a look at its graph. So we have f of x equals 0.5 raised to x. Then we have minus 2. So we can see here that as our value of x increases, our value of y from positive infinity approaches -2. And that means it is decreasing. So again, if our value of a is a decimal number greater than 0 but less than 1, our graph is decreasing and it looks like this. Alright? Now let's compare our two examples. So first, our first example is y equals 5 raised to x. And our second example is y equals 1/2 raised to x. In our first example, our base is greater than 1. And for our second example, our base is less than 1 but still greater than 0. Our first example, that is the red line. Looking at this example, we can see that as our x increases, the value of y also increases. So it is increasing or growing. However, for our y equals 1/2 raised to x graph, where a is greater than 0 but less than 1, we can see that as x increases, y decreases. Or it is decreasing, or in other words, decaying. So we can see that if a is greater than 1, the graph will look similar to this, the red one. And if the base is less than 1, basically it looks like, or it looks similar to this graph, which is decreasing or decaying. And that's the end of our lecture. What we learned how to graph an exponential function. We supplied the missing values in a table of values of exponential function. We determined the parts, trends, restrictions, and characteristics of an exponential function. In our next video, we will learn about the domain, range, and intercepts of exponential function. For supplementary problems, you may refer to QuexBook General Mathematics Chapter 3.